In this class, you will learn more about IPSec VPN, including how to implement complex VPN topologies. It assumes you are already familiar with IPSec VPN basics taught for the FCNSA certification. IPSec VPN overview and terminology, Diffie-Hellman, quick mode selectors, policy-based versus route-based VPN, configuring point-to-point VPNs, and VPN monitor. In this class, we will teach main mode, aggressive mode, NAT traversal, extended authentication, VPN topologies, dial-up VPNs, IKE mode configuration, and redundant VPNs. We'll also learn how to troubleshoot IPSec VPN tunnels. After this class, you will be able to describe the components and protocols of the IPSec standard. We will explain how to choose between main mode and aggressive mode. You will also be able to implement different VPN topologies, such as dial-up connections between two FortiGate devices, dial-up connections for FortiClient, and redundant VPNs. As we saw in the class for basic IPSec VPNs, on FortiGate, IPSec both authenticates and encrypts network traffic passing through FortiGate. Although the standard acknowledges the possibility of expansion, in practice, the three most used protocols are Internet Key Exchange, known as IKE, which does the handshake, tunnel maintenance, and disconnection; Encapsulation Security Payload, ESP, which ensures data integrity and encryption; Authentication Header, AH, which offers only data integrity, not encryption. Each tunnel uses either ESP or AH to act as the transport for the packet payload. However, FortiGate and most other vendors' IPSec devices only use ESP, not AH. This is because, in practice, people who make the effort to deploy a VPN want not just data integrity, but privacy. Since we'll expand first on IKE, let's review a little about the key exchange, which uses port UDP 500 and, if NAT is enabled, UDP port 4500. IKE is the first step of establishing an IPSec VPN tunnel. FortiGate uses it to negotiate with the client and determine the security association, known as an SA, the authentication, keys, and settings that will be used to encrypt and decrypt that client's packets. It is based on the Internet Security Association and Key Management Protocol, known as ISA-KMP. Each SA is direction specific, so in two-way traffic, there are two SAs per tunnel. As explained during the basic IPSec VPN class, IKE defines two phases. In phase 1, there are two possible negotiation methods, main mode and aggressive mode. Phase 2 only has quick mode. So now, let's study the differences between main mode and aggressive mode. This shows main mode. 6 packets are exchanged. First, the client initiates by proposing that the tunnel will use one or more security policies. The responder selects which security policy it will agree to use and replies. Then, the initiator sends its key. The responder replies with its own key. Finally, the initiator sends its peer ID and hash payload, and the responder replies in the same way. Initially, the responder can only identify the initiator by the source IP address, nothing else. This is because the initiator's peer ID hasn't been established yet. That works for point-to-point VPNs because both ends have static IPs, so the responder can predict the client's ID and knows which security policies to propose, even if you have configured multiple possible VPN settings. It's also okay for a dial-up VPN where you've configured only one phase 1 The responder can't predict the IP address of its peer, but only one proposal is possible. However, it is a problem for a responder to have multiple possible proposals and multiple possible peers. Then it can't predict which client is connecting at that IP. So it also doesn't know which is the appropriate tunnel configuration to propose for each incoming connection attempt. So main mode isn't appropriate there. In comparison, let's show aggressive mode negotiation. Only 3 packets are exchanged. First, the client initiates by suggesting a security policy and providing its key and peer ID. The responder replies with the same information plus a hash. Finally, the initiator sends its hash payload. So, unlike main mode, the first packet does contain the initiator's peer ID. Therefore, the responder can use this ID and not only the source IP address to know who the peer is and which security policy to use. It doesn't require a static source address, nor only a single VPN configuration. IKE Phase 1 has more options that we didn't discuss during the basic IPSec VPN class. After FortiGate completes the key exchange, it will apply ESP to encrypt packets. Before we mentioned that ESP is IP protocol 50, not UDP protocol 17, nor TCP protocol 6. Unlike TCP and UDP, ESP doesn't have source or destination port numbers. Therefore, ESP often can't cross through NAT devices such as firewalls that use port forwarding. To solve this, IPSec was extended with a feature called NAT traversal, also called NAT-T. When NAT-T is enabled on both ends, peers can detect any NAT device along the path. If NAT is found, then both Phase 2 and remaining Phase 1 packets change to UDP port 4500. FortiGate and Client encapsulates ESP within UDP port 4500. Another advanced Phase 1 option is XAuth. In the basic IPSec VPN class, we mentioned that Phase 1 supports 2 types of authentication: pre-shared keys and digital certificates. The XAuth extension to IPSec requires that between Phase 1 and Phase 2, clients also must supply a username and password. So additional packets are exchanged if you enable it, making tunnel startup slightly slower, and you must configure FortiGate for user authentication, but the benefit is that it strengthens authentication. While showing how to choose between main mode and aggressive mode, we briefly mentioned effects of static versus dynamic IP addresses. Let's discuss that a little further. When configuring Phase 1, we must specify the type of remote peer. There are 3 types: static IP address, self-explanatory; dynamic DNS is where the peer's IP is dynamic, but the ability to resolve it through a static DNS name makes it, in effect, a static peer. For example, branch offices often use DHCP from an ISP. The IP address changes, but not often. So we could use dynamic DNS to get a static DNS name that resolves to the dynamic IP. Then we configure FortiGate with the peer's DNS domain name, which it will query to resolve. Dial-up is, unlike its name implies, not necessarily through a dial-up modem. It's where the peer's IP is dynamic, but there is no dynamic DNS. This is often true for branch offices, satellite campuses, and FortiClient VPN clients. Can these peers ever receive a VPN connection request? No, because they are a moving target, and unlike dynamic DNS peers, there is no way to find their current location on the IP network. Now that we've seen some effects of dynamic versus static IP addresses on configuration, let's expand and see possible topologies with those. There are 5 types: point-to-point, dial-up, hub and spoke, full mesh, partial mesh. Point-to-point VPNs are simplest. Two peers basically communicate directly. This topology and how to configure it was covered in the basic IPSec VPN class. Now let's see the other 4 topologies. First, here is a dial-up VPN. Its geometry is simple. Dial-up VPN is used when you don't know where the remote peer will be connecting from, such as with traveling employees with FortiClient on their laptops. Unlike site-to-site VPNs, one dial-up VPN configuration on your FortiGate can be used for multiple IPsec tunnels with many remote offices or users. Hence its other name, point-to-multipoint. Keep in mind that in dial-up, the client's IP is dynamic, so FortiGate can't predict where it will be. That means that FortiGate cannot initiate the VPN, only the remote peer can. One point-to-multipoint topology variation is called hub and spoke. Its name describes how all clients connect through a central hub, similar to how spokes connect to hubs on wheels. In this example, the clients, spokes, are each branch office's FortiGate. For any branch office to reach another, its traffic must pass through headquarters. An advantage of this topology is that the VPN configuration and firewall policies are easily managed. They exist mostly on the central FortiGate. System requirements are also minimal for the branch office FortiGates, since each only needs to maintain 1 tunnel, 2 SAs. In total, only 4 tunnels, 8 SAs are required. A disadvantage is that especially if headquarters is physically distant, like it can be for global companies, communications between branch offices through headquarters will be much slower than a direct connection. If your headquarters is in Brazil and you have offices in Japan and Germany, latency can be very significant. If the FortiGate at HQ fails, VPN failure will be company-wide. Also, the FortiGate at headquarters must be much more powerful. It must be able to handle 4 tunnels simultaneously, 8 SAs. So what would a topology look like if some or all branch offices could bypass headquarters and connect directly to each other? These are meshed VPNs. 2 variants exist. Full mesh connects every location to every other. Here, like the previous hub and spoke example, there are only 5 locations. But to fully interconnect, every FortiGate requires 4 VPN tunnels, 8 SAs to the others. This is 3 more tunnels per FortiGate than most FortiGates in hub and spoke. In total, 20 different VPN tunnels are required, not 4. If you expand to 6 locations, it would require 30 VPNs, 7 locations would need 42, and so on. So this topology's advantage is that it causes less latency and requires much less headquarter bandwidth than hub and spoke. But its disadvantages is that every FortiGate must be more powerful than the average FortiGate in hub and spoke. Partial mesh attempts to compromise between the 2 advantages and disadvantages, minimizing required resources but also keeping latency to reasonable levels. Partial mesh can be appropriate if communication is not required between every location. However, notice that each FortiGate's configuration is still much more complex than hub and spoke. Routing especially may require extensive planning. So generally, the more locations you have, hub and spoke will be cheaper but slower than a mesh topology. Mesh will place less strain on the central location and be more fault tolerant but more expensive. To review, here is a quick comparison. Each topology has its benefits and trade-offs, so you should choose the one that is the most appropriate to your situation. Now that we've shown the topological differences, let's look at how these are configured. Before we said that hub and spoke, full mesh, and partial mesh can be built using a combination of point-to-point and point-to-multipoint VPNs. Point-to-point configuration was shown in the basic IPSec VPN class, and dynamic DNS is a slight modification of that. So let's configure point-to-multipoint, called dial-up VPN, on the GUI. Notice that the steps are the same. What is different? The settings. For each peer, we must first configure phase 1, second, configure at least one phase 2. In this topology, you can have multiple corresponding to the multiple peers. Third, configure firewall policies. Last, you may need static routes or a dynamic routing protocol. That way, once a peer joins the VPN and receives their virtual IP, its traffic can be routed through the VPNs. Remember, there are two different ways to bring up the VPN on the FortiGate: policy-based or interfaced, also known as route-based. For policy-based VPNs, additional routing entries are usually not required. Only one bidirectional firewall policy is required. For interface-based VPNs, at least two firewall policies are usually required, one policy for each direction. If your spokes are FortiClient installations and it's a route mode VPN, then often you will want to enable and configure mode config on the hub's phase 1. This is for an IPSec extension called IKE mode configuration. IKE mode configuration is a more practical alternative than to allocate static IPs to each of the many laptops and mobile phones, for example. Like DHCP for VPNs, mode config automatically configures the client's network settings. Like with DHCP, you define a range for the pool of VPN virtual IPs, the DNS settings, and the client's gateway router. Remember, these settings are all for the virtual network, not their local LAN, so they'll usually be different. Let's start by configuring a phase 1 for the hub in a hub and spoke. Since hub and spoke topology is a variation of point-to-multipoint, remote gateway must be set to dial-up user. If each spoke requires a different policy, then usually we must configure multiple dial-up VPNs. Remember, this requires IKE aggressive mode, which in turn requires both the key and the peer ID. Main mode key exchanges don't support one-to-many topologies. Next, when we configure the spokes, the spoke FortiGate or FortiClient on the other end of the VPN tunnel must use the exact same ID. The hub identifies each spoke by its peer ID and applies corresponding VPN settings. To strengthen authentication, you can enable extended authentication. The hub FortiGate will use the Enable as Server setting. Each FortiClient or spoke FortiGate will use Enable as Client. Then we select the user group that contains all the users and credentials that will be accepted by this VPN. NAT traversal should be enabled if your spokes are mobile dial-up users, because they are usually behind NAT at airport terminals, home routers, and hotel firewalls. In this case, you'll often want to enable mode config too. Lastly, on the hub, configure phase 2. Usually, the quick mode selector is 0.0.0.0/0 for both source and destination. This matches any connecting IP. Next, let's configure a spoke. This is phase 1. First, specify whether the hub for this spoke is using a static IP or dynamic DNS. If the mode is set to aggressive, then in the local ID, enter the name that this spoke will use to identify itself to the hub. This ID must match the one that we configured on the hub. If you enable XAuth on the hub, you must enable XAuth on the spoke too and configure the username and password. Finally, this is the spokes phase 2. For the quick mode selectors, the source address must be the hub's internal network. For interface-based VPNs, the hub will automatically add a static route to this subnet from the spokes IP immediately after the VPN is established. That way, you don't need to manually configure the hub FortiGate with all static routes for each spoke. The destination also must be the hub's local network, but unlike the source network, for this, you must manually add a static route to this network on the hub FortiGate. It's not added automatically. Note that unlike with point-to-point VPNs, the quick mode selectors for point-to-multipoint do not need to mirror each other. If your clients are FortiClient, there are simpler alternatives to configure your spokes. On FortiGate's GUI, in the IPSec VPN area, there is a FortiClient VPN configuration wizard. Just enter basic settings such as authentication method, pre-shared key, user group for extended authentication, and IP setting, or mode config. The wizard creates both phase 1 and phase 2. It's interface-based and uses aggressive mode, XAuth, and mode config. Note, though, that the wizard doesn't apply it to a firewall policy. It doesn't add a static route either, so remember to do that after using the wizard. We mentioned briefly that hub and spoke is inherently not fault tolerant. If the hub fails, then all VPN tunnels are down. How can you make your hub and spoke IPsec VPN more resilient? Provide a second ISP connection to your hub and configure 2 interface-based VPNs. If the primary VPN fails, another tunnel can be used instead. 2 types of redundant VPNs exist. Partially redundant, on one peer, usually the hub, where a backup ISP is available if the main ISP is down. Each VPN terminates on different physical ports. That way, FortiGate can use an alternative VPN if, for example, ISP1 or WAN1 fails. But on the other peer, usually the spokes, both VPNs terminate on the same physical port, so the spoke is not fault tolerant. Fully redundant, both peers terminate their VPNs on different physical ports, so both hub and spoke are fault tolerant. So how can we configure a partially or fully redundant VPN? First, create one interface-based phase 1 for each path, one phase 1 for the primary VPN, and one for the backup. Enable dead peer detection, DPD, so that FortiGate will detect when the VPN tunnel to its peer is down and switch to route traffic through the backup VPN. Create a phase 2 also. Because they are interface-based VPNs, we must add at least one static route per VPN. Routes for the primary VPN must have a smaller distance than the backup. This causes FortiGate to use the primary VPN while it's available. If the primary VPN fails, then FortiGate automatically adds the backup routes, which have a slightly larger distance and wouldn't otherwise be used, to the routing table. Alternatively, by the way, we could use a dynamic routing protocol such as OSPF or BGP. Finally, configure firewall policies to allow traffic through both the primary and the backup VPNs. Since these are interface-based VPNs, at least 2 firewall policies are required per VPN, one for each direction. As you can see, IPsec VPN configurations can be very complex. What is the best way to solve problems? When troubleshooting, look for setting mismatches first. Most connection failures are due to misconfiguration. Is a route missing? Is a firewall policy missing or blocking the traffic? Are VPN settings mismatched? If settings are correct, then you'll enter most diagnostic commands on the responder FortiGate's CLI not the initiators. This is because from the initiator side, you can only see what the initiator sends. You cannot read the responder's console, which would have messages that indicate why it had refused the connection. In comparison, the responder can see both the initiating packet and the responder's own decision and response, if any. If both sides of the VPN can reach each other to bring the tunnel up, then look for routing problems within the virtual network. Remember that once a peer joins the VPN, it has another IP address within the virtual network. If routes don't exist to allow traffic to be routed between those VPNs, then communication inside the VPN will fail, even though its containing tunnel is up. If settings are correct, you can use the command line to display details of the VPN tunnel as it occurs. Run diag debug reset before and after each diagnostic session to reset and enable other IPSec diagnostic commands. They don't usually significantly impact the CPU. However, you should always disable them after finishing the troubleshooting because logging out will not stop a diagnostic command. The filter command restricts debug logging to IPSec traffic from a specific remote peer. There are many different filter options. If the problem is a tunnel that is not coming up, you should filter based on the initiator's IP address. After the filter is set up, you enable the IKE application debug with the value 255 to see all output. The output from the debug command is extensive. It details phase 1 and 2 negotiations. We will not show the whole output here, but the next two slides will show the most important messages you should see if everything is okay. This shows some output for a successful phase 1 negotiation using main mode. The first line shows the arrival of a VPN connection attempt from the IP address 172.20.187.114. The third line shows that the packet received was the first main mode packet. A bit later, the debug shows that FortiGate accepted the SA proposal from the remote peer. It shows the name of the phase 1 that matches the proposal. In this case, it's the name remote. FortiGate replies to the first main mode packet, then the second main mode packet arrives. FortiGate replies again, and the third main mode packet is received. After finishing negotiation, the output will display two messages. They indicate that the key exchange was successful and SA was established. Let's see what is displayed during the phase 2 negotiation. Again, the output is much longer than this. The slide only shows a sample of some parts of that output. The first line announces the arrival of the first quick mode packet. The second line shows the quick mode selector proposed by the remote peer. In this case, it is 0.0.0.0/0 for both the source and destination. Some lines below, the debug displays the quick mode selector that was successfully negotiated between both peers. The last two lines finally show that the tunnel is up and that the phase 2 SA is established. If there are any problems in the establishment of either the phase 1 or phase 2, the output to the console shows the problem. If the tunnel is up but the traffic is not passing through the VPN, we can use diag debug flow CLI command to troubleshoot. This will display step by step what each FortiGate module does with each packet. With the first command, diag debug flow filter, set the filter that identifies which traffic to monitor. For IPSec, we usually filter with a valid IP address in the remote site. Then we enter the other four commands and send traffic to that remote IP address. For example, we can try to ping the remote IP address from our local site. If successful, we should see an output similar to this. This line indicates that the packet was encrypted. The other line indicates that the encrypted packet was sent to the tunnel with the name HQ. If there is a problem either encrypting or routing the packet, the output of this command will show the problem. Now it's time for the labs. There are 2. The first lab has 7 exercises where you will configure and test a semi-redundant VPN topology using OSPF over IPSec. The second lab, which is optional, has 3 exercises where you will configure a dial-up VPN on FortiGate for FortiClient users.